Hello. Okay, so that's happening. But I don't see the things. Oh my goodness, people are watching and now nothing's working. This is like my worst nightmare. Oh, awesome, but the sound is working so they can hear me freaking out. Okay, so I've done the thing again. And now everyone can see me? Or not me, but my things. Yay, okay. Hello. So I worked really hard on getting a graphic that had lots of eager in it, and then my partner criticized me. But I said that my students would be on board. So Eager and I welcome you. Hello. And today we're going to go over Test 5, and it's going to be amazing. Oh my goodness, I have 3 people watching now. This is so exciting, guys. Thank you. Okay. So, I'm going to start by going over the integrals. They didn't go great, but given that this was your first test with the 2 techniques that we have, I think that you did about as well as anyone I've ever seen has done, so try not to beat yourself up about it. So cosine of the square root of x over the square root of x. We have a function on the inside, so this is going to be a u-sub problem. Wait, what happened? Oh, there we go. So this is going to be a u-sub problem. We're going to let u equal the square root of x. And just so we remember, this is x to the 1/2, right? So then du is the derivative of that. And remember, when we take the derivative, our exponent goes down by 1. So we're going to multiply by the exponent and then drop the exponent down by 1. So 1/2 minus 1 is negative 1/2. And we often write this as 1 over 2 root 2. And then we'll include times dx, which is the chain rule. And we can see that's even in the problem, but just so we're consistent, I'm going to go ahead and solve this equation for du. So I'll get, and some of you are like, what's going on? Why is it root 2 and it's not? It's root x. You're right, I'm wrong. Just kidding. But now when we do this and we solve for dx, we'll get 2 root x equals du. I'm sorry. 2 root x du equals dx. There we go. So now we can rewrite this integral as the integral of cosine of just u. Now if we wanted to, we could rewrite that square root of x as u as well. We wouldn't be wrong in that case, but I'm just going to leave it as the square root of x because when I replace the square root of x with what it equals to, the dx with what it equals to, the square roots of x will cancel. But if I had replaced it with u, I would then replace that square root of x in the top with u as well, so they would still cancel. So don't worry too much if you decided to sub a little more than you needed to. but now this is 2 times the integral of cosine u du, and the integral of cosine is positive sine of u, and I'll throw a plus c in there. And now u is an auxiliary variable, and I don't want to have an auxiliary variable in my answer, so this is just 2 sine of what u equals, which is root x plus c. So that's our final answer. And a lot of you, but not all of you, did okay with this one. This was pretty a confidence booster for a lot of you. So good job there. But things did start to get a little tricksy on the next one. So this has a little bit of a weirdness about it. So this is an integration by parts problem, and it's going to have a u sub in it as well. So I'm going to use the form of integration by parts that's f times g minus the integral of gf prime. And so f is going to equal x, and g prime will equal sine of 2x minus 3. And I need that product to be exactly what's in the integral. Now some of you are saying, but we have an inside function, why aren't we doing u sub? And you totally could, and in fact we will need to find g, but I'm going to wave my hands on that, and we'll have to do exactly the same u substitution a little bit later. So in this case, if I let f be x, f prime is dx, and then g is the antiderivative of sine of 2x minus 3, which is negative cosine of 2x minus 3 all over 2. Now that over 2 is what you get from u substitution, and we'll talk about where it comes from a little bit later when I do a different integral, but it's very, very similar to this one. So let's sub in what we have to our integration by parts. I'm kind of wondering if you guys can hear my neighbor's loud car. But here we go. This is what I get when I sub in f, g, and f prime into my integration by parts. And you can see that I'm taking the antiderivative of cosine of this same expression. I'm going to clean it up and get the integral just a little bit nicer before I integrate. And this leading part can be a little bit nicer as well. You don't have to clean it up, but since I'm going to be rewriting it a lot, I will. And so now I need to finish by taking cosine of 2x minus 3. So that is the same u sub that I would have done to find g from g prime. It's just I'm taking the integral of cosine now rather than sine. So I'll let u be 2x minus 3. And then u is just 2x dx, which makes du over 2 equal to dx. All right, so that's what I'm going to be subbing in. And then I'm rewriting what I had before. So this is just cosine of u times du over 2. So that's also where this over 2 here came from. I don't know if you can see that. But that's why we have that 1/2 hanging out. I can pull that out of my integral before I integrate just to make everything a little bit nicer. And now I'm just taking the antiderivative of cosine of u, and that is positive sine u, so I have 1/4 positive sine u plus c. When I was initially writing this up, I wrote negative sine u, and then I had to erase it. You can even see like the little gap where the minus was. I screw it up too, but try to get it straight for one more day, and that day I believe is next Thursday. And then I'm going to sub back in for what u equals now, and I am done. Oops. There you go. Let that sit there for a little bit longer. So again, I could have started with u sub, and you might have seen me do that a little bit before. It ended up taking more writing than if I had done it this way. So this is the way I wanted to show you, where the u sub is done inside the integration by parts. So next is this one. This, you guys actually did a lot better than I thought you would. This is kind of a scary antiderivative, I think, and most of you tackled it very well. You recognized that it was a u substitution problem right off the bat. So if you let u be just the denominator there, then it just so happens that du is exactly the numerator. Typically we don't worry about putting what dx is multiplied by in the parentheses. We just assume that it's being multiplied by everything in front. But just to be really explicit, because some of you were screwing up parentheses a little bit and it messed you up. So now I'm going to solve for du. Or I'm sorry, I'm just going to pull out that -1 to make du equal to exactly the numerator times dx. And then I'll solve for dx in terms of du and e to the -x. So that when I rewrite this guy, I've got a u in the denominator, I've got the rest of the numerator, but then that dx becomes du over e to the x plus e to the -x, and they will die a cruel and horrible death. So now my integral is just du over u, and this is just the natural log of u plus c. Now, a lot of you are using natural log a little bit more than you're supposed to, and we'll talk about that in the next problem, but this is actually a natural log question, and u is an auxiliary variable, so just to get rid of that, I'll replace it with what u equals. And then I wrote dx for some reason. That's kind of embarrassing, but it should just be a plus c. Is that okay? Okay. So we're almost there. I think this was the last antiderivative that you had. But this is kind of where things went south for you guys. So most of you realized that this was an integration by parts problem. But when you were finding f and g prime, a lot of you said that g prime was equal to x squared. You're confused about the -1. I shall go back. How do I go back? There we go. You're confused about the -1. So I'm going to guess that the -1 you're talking about is this one here. And that's from the derivative of the inside. So when I'm taking the derivative of e to the x, or e to the -x, the derivative of e to the -x is equal to the derivative of the outside function, which is just e to the -x, but then times the derivative of the inside. But the derivative of -x is just -1. And then because it's just -1, I can pull that minus to the front there. chain rule eludes all of us sometimes. Don't feel bad about that. All right, great question. And thank you. I'll make a note when I make this into a video to post later to highlight that point. Okay. No, I gave away the punchline now. All right. So, is everybody good here? I'm jumping back ahead with what I'm choosing for x and what I'm choosing for g prime. And do you understand why it's not okay to pick x squared to be g prime? There's a couple of second delay, so this pause is very dramatic. But at this point, I'm going to assume that everything is fine. But I'm keeping an eye on the chat, so just jump in if you need to. So now, oops. Let's keep going. F prime is just 2 over x dx. That's the derivative of ln. And remember that g prime is equal to dx over x squared, so that's the same as x to the negative second times dx. So when we take the antiderivative of x to the negative second, we take negative 2, add 1 to it, so that negative 2 becomes a negative 1, and then we multiply by the reciprocal of negative 1, or divide by negative 1 in this case. And so this will simplify to negative 1 over x. Okay? So it's the reverse power rule. So when I replace everything in the integration by parts with what I've assigned to it, it looks like that. And now I'm just going to clean stuff up, combine minus signs, combine x's, and what have you, to get a nice, a nicer expression here. So I pulled that 2 in the integral out front, I pulled the minus sign out front, so the 2 minuses combined and made a plus. And then I had this minus here that I pulled out here. Okay? So, and the only reason I do that is for bookkeeping purposes. If you are good enough to be able to skip this step, power to you. But we've all seen what happens when I don't do that. So now rewriting what we had before, it looks like this. And now the antiderivative of x to the negative second we already did. It's 1 over x, and then I'm multiplying by 2, so this 2 is this 2. This minus came from the negative 2 becoming negative 1, and multiplying. So most of this is just the same as I had over here. Okay? And so now, because I had no u sub, I don't need to sub back in, this is my final answer. So take a second and try to figure out what went wrong for you on the test, and then chime in if it's not clear what you should have done or what I did. All right, so I'm going to move on. And this next one is Professor Leopold's, but I stole it from her. R of t lowercase r is the rate that water is flowing out of a faucet. And it's in the units quarts per minute. And so given that there is 1 quart of water in the sink initially, so that's kind of like your initial condition, what is the amount of water in the sink after 8 minutes? So you have some water in your sink, but like it's not enough, so you turn on the faucet, you get more water in your sink. And then after 8 minutes, you turn it off. You probably call a plumber as well, but whatever. Because who leaves a sink running for 8 minutes? But you want to know how much water is in there. So some of you did this as an indefinite integral, or a definite integral from 0 to 8, which was a great intuition, but you forgot about the initial condition. So if you wanted to do it as an antiderivative or a definite integral of lowercase r of t from 0 to 8, that'll tell you how much the water changed in that 8 minutes, but you'll have to add the 1 quart that was in the sink. But that's not how I'm going to do it. So let's remember that r is the derivative of the water in the sink at time t. And so I'm going to make capital R equal to the amount of water that's in the sink. And what that tells me is that the d capital R dt is equal to this lowercase r. And now this is a separable differential equation. So dr equals r of t dt. And then when I replace r of t with what it equals, I get this, and I can integrate both sides. Okay? I'm just assuming that everything is okay. Now, integrating the left-hand side is pretty easy. I think you can do it. But the right-hand side requires a u sub, or at least requires me to do a u sub. So the left-hand side integrates to just capital R. There's a constant, but I'm going to put the constant on the right-hand side. But when I do the u sub, I get that this is the integral of u to the negative 1/2 du. And now I'm going to use reverse power rule. I'm going to bump the exponent up by 1, multiply by the reciprocal of the exponent, and then add a plus c. And then replace u with what it equals. So I get that r as a function of t is 2 onto the square root of 1 plus t plus c. But now I need to use that initial condition to find out what c is. So the initial condition tells me that I have 1 quart of water in the sink and when t equals 0. So r of 0 equals 1. And now I'm going to set 1 equal to my expression and plug in 0 for t. And that tells me that negative 1 is equal to c when I solve that. All right? So that means that r as a function of t is equal to 2 onto the square root of 1 plus t. I'm replacing c with negative 1. And then when I plug in 8, I get my answer. All right. I don't think I'm going to be a professional YouTuber after all. This is really hard. And I think when I simplify that, I get 6 minus 1, which is 5. So my answer is 5 quarts. That seems like a lot of water to have in a sink, but there we go. Okay. Next, we just give you a differential equation and we tell you to solve it using separation of variables, and we ask you to show all your work. Understand the math, but we're confused about the logic behind this problem. So, are we clear that lowercase r is a derivative? Because that's the real thing. We want to remember that lowercase r, the expression given to us, was a rate. So that's like telling us how fast we're going, or I guess how fast we're going is really the only derivative that I've internalized. But it's like telling us the speed at which something is happening. So if we wanted to figure out how far we had traveled, and we know how fast we're going, we can integrate our speed to find our total distance traveled. So that's essentially what we're doing. We're integrating the speed that water is entering the sink to figure out how much water we have. So when we integrate, we're using an indefinite integral here. We get an arbitrary constant plus c, and that's why we have to use our initial condition, because in this case our sink wasn't empty. It had a quart of water in it. And so when we solve for c, taking that into account, we get that c equals -1. So using the antiderivative to get the amount of water in the sink over time can be off by a constant. So we need to use the initial condition that they give us to figure out what that constant is. Just like if we have my speed based on my Fitbit that I'm walking, and it tells me that, my speed is 3 miles per hour, if you were trying to use that information to find out where I was at the end of my hour of walking at that speed, it would depend on where I started, right? It would be different if I started from my house than if I started from Northeastern. So that's why we had to find the C. Also, thank you, Kefi, for being the only person watching my YouTube channel and being active. You're my new favorite student. So the one after this, number 4 on the test, capital R, I just, I made up, and it represents the amount of water that's in the sink. So I said that I'm going to let capital R be the amount of water in the sink, because it's related to lowercase r, but they're not the same function. But this letter I just made up because they didn't actually tell me what they wanted this to be. Sweet. Alright. So this is just a straight separation of variables problem, and it just has all the math that you said you're okay with, but I'm still going to go through it in case we have a silent viewer who is confused. So here's my differential equation, and the big issue that most people had on the test was that they tried to subtract 0.1 Q from both sides, but everything in this expression needs to be multiplied by dq or dt before we integrate both sides. We can't integrate unless we have a dq or a dt involved. So I am going to divide both sides by this whole expression on the right, -60 plus 0.1q, And I'm going to multiply by dt. And I'll get, I'm so bad at this. And I'll get that dq over that whole expression on the right equals dt. Now I'm free to integrate both sides because I have everything multiplied by some dq or dt, some infinitesimal. The left-hand side, I'm going to want to do a u sub. So I let u equal to the denominator. So the du is 0.1 times dq. And a lot of people skip this step, which is fine. But because there are like reciprocals and stuff involved, I get confused. So I never skip it. So when I solve for dq, I get du over 0.1 equals dq. Now, when I simplify that, I get this guy. That 1 over 0.1 can come out. 1 over 0.1 is 10, but I'm going to end up multiplying it on the other side, so I'm going to leave it there for now. And I get ln of u over 0.1 is equal to t plus c1. I'm just calling it c1 because rather than doing additional math to these arbitrary constants, I'm just going to rename the constant over and over. So you'll see what I mean in a second. So for the next, I'm going to multiply both sides by 0.1. And I get ln of, I plugged in what 60 equals. Ln of negative 60 plus 0.1q equals 0.1t times 0.1c1. But 0.1c1 is just some other arbitrary constant. So this guy is just 0.1c1. But why would I write that? It's a new arbitrary constant. I'll give it a new name. I don't care. All right? So from here, now that I have my new arbitrary constant, because I don't really care what the old one was, I just care what the final one is going to be, I'm going to take e to both sides to get rid of the natural log. So I get the inside of the natural log equals e to the 0.1t plus c2. And I put a plus or minus there so I didn't have to worry about those absolute values, but I'm going to get to drop that plus or minus in a second, because this will simplify to plus or minus e to the 0.1t times e to the c2. And I can just think of that as, if I rewrite this as plus or minus e to the c2 times e to the 0.1t, then I can treat this plus or minus c2 as an arbitrary constant on its own. And I can just rename it C3, which is what I'm going to do. Okay, so that's going to become my C3. And I'm going to backspace through all this because I think I might have written over that space later. But this is now C3 e to the 0.1t, and that C3 is plus or minus e to the C2. But it doesn't matter what that was, what the C2 was. It just matters what the C3 ends up being. I tried really hard to get a PO, so I could be talking about C3PO, but didn't work out. So now I'm going to solve for Q. I have to add 60 to both sides. I have to divide by 0.1. When I distribute that 0.1 through, right, it's going to be C3 over 0.1 plus 60 over 0.1. This 60 is going to become 600. And that C3 over 0.1 is going to become something else. I'm just going to call it C. And now I can apply my initial condition. I know that Q of 0 equals 0. So I'll set Q equal to 0. I'll plug in 0 for T. And then e to the 0 is just 1. So I get C plus 600 equals 0. So C equals negative 600. I just get to plug that in and I'll get my differential equation. And there it is. Final answer. So just for reference, this guy here was the general solution. Sometimes we ask you for the general solution, and that is the solution before we find out what C is. And then this guy here that I boxed, that's the particular solution. If we give you an initial condition, we want the particular solution. All right. So be sure you understand this math. This type of problem is definitely going to be on the final. And the arithmetic or algebraic manipulation is going to be the same for everybody. Igor is not impressed with my presentation skills. He would much rather I be playing fetch right now. Alright, now, this one is my favorite one because it involves liquid nitrogen. We have a mineral compound immersed in liquid nitrogen, and the temperature of that mineral compound after we drop it in the liquid nitrogen is given by this differential equation. And now what I'm thinking of when I think of this problem is Dippin' Dots ice cream, because they just take the ice cream mixture and they drop little dots of the, like cream into liquid nitrogen, and it makes these little bubbles. And that's what Dippin' Dots is. So that's what you should have in your mind when you're thinking about this equation. So what is the equilibrium solution going to be? Well, the mineral, whatever we're dropping into the liquid nitrogen is going to get pretty darn cold. So it's going to be close to whatever the temperature of the liquid nitrogen is. Is it going to be stable or unstable? Well, we certainly don't think that the mineral that we drop into the liquid nitrogen, regardless of what its temperature was when it was dropped in, its temperature isn't going to shoot up to positive infinity or go down to negative infinity, right? So it's, the solution is probably going to be stable, all right? So for part A, they ask you to find the equilibrium solution. And I joked in my class that, a lot of you guys just weren't thinking after problem 1. And if I got asked a whole bunch of integrals and I wasn't sure how to do all of them, afterwards, if I asked, if you asked me what my favorite color was, there's a 50-50 chance that I would have responded elephant. I just get dumber after I get asked questions that I don't know the answer to. So I suggest when you get to your final, flip through it, answer all the things that you know the answer to first, and it's okay to answer just one part of a problem. So when you go to find the equilibrium solution, what do? You set the derivative equal to 0, because the equilibrium solution means that the function is a constant value, and constant values have slope 0. Now you're just going to solve for k. You have 65 over negative 0.2 is equal to k. Now, maybe you don't know what 65 over 0.2 is, but you know that 65 over negative 0.2 is definitely negative. Very negative, all right? So at least you have that information. And a lot of people were like, oh, I don't know what this is. And then they drew it above the x-axis. So k equals negative 325. That's what it worked out to. But the important thing to note was that it was negative. All right? And that's important for part B. So part B of this same problem asked you, if your initial condition were k of 0 equals 0, without solving the equation, use the information about the first and second derivative to sketch the solution curve. Also, include the equilibrium solution in your sketch. So here is my axis, and here is my equilibrium solution. It's important to see that it's below the x-axis. And now the other thing that people didn't include that it would have helped you a lot if you had thought about was where the initial condition is. Because the initial condition, k of 0 equals 0, that means the point 0, 0 is on your curve, right? So the origin is there. And so, like I said, it makes sense in terms of the context that this is a stable equilibrium solution. And so we want to draw a curve that's approaching the equilibrium solution as t tends to infinity, and it has to go through our initial condition, k of 0 equals 0. And so I think it's going to look that way, but I still need to verify using the first and second derivative that it does. All right. So when k is when k is greater than negative 325, a good example of a value that is greater than negative 325 is 0. What is the derivative of k with respect to t, then? It's negative. And I could think of just plugging in any number greater than negative 325 into dk dt, into my differential equation. And if I plug 0 in, then the derivative is negative 65. So the derivative is negative. So what does that mean? The graph is decreasing. All right? So I at least got the direction that the curve is going correct. Now I need to think about the second derivative. And this tripped a lot of people up. You're taking the derivative of the first derivative, and a lot of people got that right. So you're taking the derivative of this guy. But things got a little bit hairy because they forgot chain rule. So the second derivative of k is negative 0.2 times dk dt. And this is significant because the derivative of k is negative. So now we have negative 0.2 times another negative number. So we have a negative times a negative. So the second derivative is positive, right? We have a negative coefficient times the derivative of k. We know the derivative of k is negative. If we take the negative derivative of k and we multiply it by a negative number, we're going to get a positive. So this guy is greater than 0. And so our curve needs to be concave up. All right, so I've drawn this correctly. And that's all you need to do for part B. Part C asks you what's happening as t tends to infinity. Why do we have to chain dk dt? Because we are differentiating with respect to t, not with respect to k. Yeah. I'm trying to think of more of a justification than that, because that's a really good question. So we can think of this, sorry, I'm trying to control these. We can think of this as, remember, K depends on T. The temperature of this mineral compound is changing as a function of time. So the temperature depends on T. So K is actually a function, right? And so we even know what the derivative of K is. That is exactly what our differential equation is. So if we wanted to, we could even write the second derivative in terms of the first derivative. So we could even say that this is equal to negative 0.2 times what dk dt is. So negative 0.2 k of t minus 65. So we can even give an explicit form to what the second derivative is. And you can see here that it would be very hard for us to draw a curve that's above this equilibrium solution, that's decreasing, and that's concave down, right? Even if you try to, things are going to get wonky for you really quick, right? How do you draw something that is decreasing, concave down, but it's not allowed to touch your equilibrium solution? See, that's going to be really hard. So it's the fact that the first derivative that is decreasing that kind of even tells us that the second derivative has to be positive. It has to be concave up. Because if it weren't, we wouldn't, our solutions would cross. Okay. Somebody should remind me to post the link to the parody of Bohemian Rhapsody. It's a parody that's about calculus, and they have a lot of parts that are just reminding you to use the chain rule. Okay. So, sorry, I forgot I added things. Now, as t goes to infinity, k is tending to our equilibrium solution. Whatever your answer is, be sure that it's consistent with your graph. So if your graph showed you shooting off to positive infinity, you should put that down. So make sure that your graph and your answer here are consistent. And then because it's tending to our equilibrium solution, we know that our equilibrium solution is stable. So I hope that was okay for you guys. Am I right that neither one of you is a student in my class? I'm pretty sure neither one of you is a student in my class. And the implication of that is that you didn't have this last question on your exam, but you might have something like it on the final, so we can still go over it if you want. Right, but you're not in my class, right? Okay, good. It's like, I'm pretty sure I complimented the head wrap girl for having a head wrap, specifically because she wasn't in my class, and I wanted to make you guys feel welcome. I'm so sorry that you lost your instructor for a week. That must have been very sad for you guys. Okay. Anyways. So I'm going to put this last question up here. And I'll give you some time to read it over. So the idea is that we are saying that someone burns 20 calories per pound, which is a total exaggeration, or at least I don't burn that much. But your amount is equal to 20 times your weight. Okay? And now we're talking about a person who eats a constant number of calories. they start by not telling us what that constant number is. They just call it I. But you can think of I like pi. It's some number, we don't really know it, but it's constant. It is a number. It's just in the ether somewhere. So it's different than a variable. Okay. So now if we think about how your weight is changing based on what you eat, well, you take in I calories per day, and you lose 20 times your weight in calories per day. All right? So, but this is in calories. So to get it in terms of weight, we have to divide by 3,500. Because that's the number of calories that make up a pound, right? So dW dt is equal to the calories in minus calories burned and then over the number of calories in a pound. Okay. Now, when I gave this to my students, I just assumed that at least the girls in the class would have dieted before, but I'm very happy to know that your generation doesn't diet near as much as my generation does, because they had no clue what I was talking about, and I've never been happier for that. Now, what is the equilibrium solution then? Well, the equilibrium solution is what happens when you're taking in exactly the amount of calories that you burn. That's the dream, right? And so when our weight is equal to, when our change in weight is equal to 0, that is when I minus 20W over 3,500 is equal to 0. So W is equal to I over 20. Okay, and so when you're eating 20 times your weight in calories, your weight doesn't change. If you want to gain weight, you need to eat more calories than that, and if you want to lose weight, you need to eat less calories than that. Okay? So is this a stable or unstable equilibrium solution? The question just asked to decide based on the context. I like my students to answer questions in words. I usually have at least one question on my test that they just have to like think about and explain. If this were an unstable equilibrium solution, there would be a way for me to become negative 2,000 pounds. And that's like my dream weight, but realistically, that's probably not possible. If this were an unstable equilibrium solution and I ate even one more calorie than I was supposed to, then my weight would shoot up towards infinity. And I have to eat a lot more calories than I'm supposed to have my weight shoot up towards infinity. They would be delicious, but This is going to be a stable equilibrium solution as a result. Okay. Unstable equilibrium solutions are like if you have 0 zombies. If you have 0 zombies, you're not going to get more zombies. But if you have even 1 zombie, then you're going to get a bajillion zombies. Okay. So, and then they had to do some arithmetic, but that was really the point, was to set up the differential equation. That's 11.6. You guys weren't tested on 11.6. So, be sure you look over that section because it will be tested on the final. Alright? Have you guys had a chance to look over the mock exam or the practice exam? Okay, so for thinking about stability, think about what it means for... So you weren't supposed to use any math to think about the stability. You were just supposed to reason about the context of the problem. And for that, we think about, like, what does it mean for something to be stable or unstable? If I eat 2,000 calories a day, my weight is going to change up until I need 2,000 calories per day in order to maintain my weight. Right? So if that is fewer calories than I need, I will lose weight until I don't need any more calories. Until I don't need any more than that 2,000 calories. If I need less than 2,000 calories, I'm going to gain until I hit whatever weight will allow me to maintain at 2,000 calories. So there's no way to make my weight shoot towards infinity. I would need to eat an infinite number of calories to gain an infinite amount of weight. But if my calories remains constant, then my weight will approach a constant number. But we're really reasoning about, like, whether something is growing really fast or growing pretty slowly. And your weight is going to, once it gets to a certain point, taper off. You're not just going to continue gaining weight indefinitely. Eventually, you'll taper off. Even if you eat 7,000 calories a day, eventually your weight will taper off. How is the mock exam? Do you want me to go over, what else do you want to see? Optimization, that is a popular choice. Any particular type of optimization problem? 4 carrots. That is a rounding consensus right there. I'm pulling up your book so I can look in there. That way I don't have to figure out how to type it out. Alright, I got some. Do one that's a little bit easier than the one that's on the mock and practice exams, just to ramp up. Do you mean number 11 on the mock exam? Yeah, the numbers on the mock exam aren't great, so let's start with this first, but I will definitely go through that. But first, oh, there are like 3 11s on the practice, though. You need to pick one. But first, let's work on this. We have a rectangle, and the perimeter is 64 centimeters. So let's say that this top bar is the width, and then this is the length. So the perimeter, 64 centimeters, is the perimeter. And I have 2 pieces of length W, and then 2 pieces of length L. And I want to maximize the area. And area is equal to length times width. Okay. Now, the goal is to optimize area, so I want to take the derivative, set it equal to 0, and solve. That's how all these optimization problems work. But to do that, I need it to be in terms of just one variable. So I will subtract 2L from both sides. I'll divide then by 2 to get W in terms of L. So W equals 32 minus L. So now I have area in terms of just the length. I don't have the width anymore. It will help you if you simplify before you differentiate, because then you don't risk forgetting the product rule. But now the derivative of 32L is just 32. The derivative of L squared is just 2L. And so we want to find the maximum that A can be. So we're going to set A prime equal to 0. And we'll get that L equals 16. Now, we know that this is either a peak, a valley, or a place where the derivative is 0. I mean, that's what we found. But we need to check the endpoints to see which it is. So what are the endpoints? The endpoints happen when L is equal to 0 or W is equal to 0. Because we can't have negative widths or lengths. But in both of those cases, the area is equal to 0. Right? So these are definitely minimums. Area being 0 is definitely a minimum. So when L equals 16 centimeters, that must be the max. And in that case, what is the area? Because find the lengths of the sides of the rectangle giving the maximum area. So we have L equals 16 centimeters, and we'll just plug that back in here to get what W equals. So W also equals 16. So the maximum rectangle with perimeter 64 is actually a square. It's a 16 centimeter by 16 centimeter square. So you find an equation for what you want to optimize, set it equal to 0, or get it in terms of one variable. Take the derivative, set it equal to 0, and solve. Check the endpoints because one of those is going to optimize your answer. So practice final number 11. Any questions on that? Okay, so this next one is going to be very similar, but I'm willing to bet the numbers are ugly. Okay, so this is the practice test. You start with a rectangular piece of cardboard that is 3 by 5. Okay, I'm going to remove squares from the corners. So that once I take those out, I can bend along these lines, and I'll get a box, right? So the area that I'm shading in will be the base of the box, and then the side pieces will make up the sides of the box. So in order for these to line up, the little corners need to be squares and they all need to have the same length. So I'm going to label X as all of these tiny squares side lengths. Okay? Does that make sense? So the volume of this box is going to be the length times the width times the height. And the height's the easy part because it's just x. The length is going to be 5 minus 2x. And the width is going to be 3 minus 2x. Right? Because this distance here, that's just the whole length 3, but it's got 2 little x pieces cut out. So it'll end up being 3 minus the 2 x's that I cut off, and same thing with this longer piece here. It's just going to be 5 minus the little x pieces that I've cut off. Oops. So volume is what I'm trying to optimize. So I'm going to multiply that polynomial out just to make the derivative easier to take. So I get first minus 5, or minus 10, minus 6, so minus 16 x minus 4 x squared. And then this is equal to 15x minus 16 x squared minus 4 x cubed. Alright. I'm assuming you're with me there. You seem like you would have objected by now if you weren't. So now I am prepared to take the derivative. And this may be why you asked about this, because this probably doesn't factor nicely. I think that 12 should be positive, am I right there? Oh no. Yeah, it should be positive. I'm like preparing for you guys to riot on me because I am going to use a calculator to solve this because the numbers aren't nice. And now you're going to be like, but we're not going to have a calculator for the final. And so I'm going to assure you that it's okay. The numbers will be nicer on the final as a result. Nope, you're absolutely right. This is a plus as well. This is a plus. Good call. Yep, you definitely are. Everybody's taking the same final. You don't get a calculator, that's right. The numbers in the final are going to be nicer, I promise. Should you be scared? No, of course you shouldn't be scared. And your instructor has written up some of the solutions to the practice test already. You'll have some more. The mock test is already up. Those numbers don't work out great either. I made that in a hurry for my students who are considering dropping the class. It's a lot, and I'm concerned especially for you guys who are taking chemistry and biology and psychology. I think that that's too much for a human being, but all other things being the same, this final is fair, and you're all brilliant women in this case, because you're all girls. You're brilliant women who are going to be more than capable of doing it, unless you have a nervous breakdown because of everything you've put on your plate. But my dog is a therapy dog as well, so he's going to be having office hours, so don't worry. So now I went ahead and graphed V prime because the numbers didn't look nice. And it is equal to 0 when x is equal to 0.607. And okay. So which of these makes sense? All right. So let's think about the bounds for x. I'm going to go back to the previous slide that has the picture that I drew on it. How big can x be? Well, how small can x be, first of all? X can be 0. That's fine. But in that case, our box is going to have volume 0. And now x can go all the way up so that we're cutting off 2 squares and leaving no side. We could be doing that. And in that case, x is going to be equal to 1.5. But we just don't have any more cardboard, right? So that's the largest x can be as a result. So this is my domain. So now I'm going to go back to the next slide. So I said that x must be between 0 and 1.5. So that 86 is this one, right off the bat. Now, in the case of both of those, so for x equals 0 and x equals 1.5, your volume is equal to 0. So your x equals 0.607 centimeters must maximize the volume. All right, and so that is this point here. And looking at the graph of the derivative, we see that the derivative is positive, so the function is increasing. So this is a graph of v prime. The graph is increasing until it gets to 0.607. And then once it hits 607, the derivative becomes negative, so the volume will start decreasing. So you can also look at the graph of the first derivative to see that this is a local maximum. Okay? So there are a couple of different ways that you can see that this maximizes the volume of the box. either by checking the endpoints, which are here, and I guess they're off the screen, or by reasoning about what the derivative is doing. Oh my gosh, you guys are terrified. I'm not even in the same space as you, and I can sense how terrified you are. Don't worry, you're gonna be fine. I'm not going to even wait for you guys to ask. I'm going to assume you're laughing with me and not at me there. I'm just going to go ahead and move directly into the second optimization problem on the practice test. You have a box, and it has a top. And apparently, I don't know how parentheses work, but that's okay. I also am terrible at drawing. Here we go. Alright, so here is the box, and I maintain that that is by far the hardest part of this problem. So one side of the base is twice the length of the other. So I'll call this 2L and this L. And then I also have a height. So the volume is equal to 64 inches. Oh man, I screwed up so much here. That should be 64 cubic inches, because it's the volume. And that is equal to 2L squared H. And so in that case, this is our constraint equation. And then the surface area is equal to, let's see, we have two sides of length of area 2L times L plus two sides of length 2L times H plus two sides of area L times H. And that makes 6 sides, and that is how many sides a box has. I'm going to spend a lot of time writing this out while you guys start typing your questions. Because setting this up is by far the hardest part of these problems. Down. Okay. Alright, but if you can get here, you're pretty solid. Now, I'm going to use this equation to solve for h in terms of L. I think that that's going to make the math a little bit easier, so that's why I'm choosing to solve for h, but if you wanted to solve for L, you wouldn't be wrong. You would just have a square root. Now I can substitute that in. And I get that the surface area is equal to 4L squared plus 6 times 32, what do I think that is? 192 over L. M6 is 18, so 180 plus 12, yeah, 192. Now, in this equation, or in this problem, we're looking to minimize surface area. So now we're going to take the derivative of surface area, set it equal to 0, and solve. So when I set this equal to 0, everything is going to work out. Not just in this problem, in life. Everything is going to be fine. And so, I make this a little bit smaller so I have a little more room. That's really why these problems are easier for me than you guys, because I don't have to worry about page space. So 24 equals L cubed. And I think that that is saying that L equals 2 onto the square root of 3. But you can just, or the cubed root of 3. Or just the cubed root of 24 equals L. That's fine too. So that means our dimensions are the cubed root of 24, what we just found. That's this side. That one. Plus twice that, because that's what the problem gave us. I'm sorry, not plus, just cross by. And then by h, which we get by plugging this guy into our equation for h here. So by 32 over the cubed root of 24 squared. Final answer. You can also consider the endpoints, and that would be where L is 0, which really doesn't make any sense because then you don't have 64. Well, then you don't have 64 ounces or inches, cubic inches of volume, but you know, like that's what the minimum is approaching. Or when H is equal to 0, so that's basically when L is equal to infinity. How do we know to find the endpoints and graph the derivative and find the maximum and minimum? So the only reason, I'll go back to that problem and we'll talk about it. The only reason we had to do this, where we graphed it, was because I didn't know how to factor this beast. And I don't have a calculator on me. Why does it keep doing that? Oh. And I don't have a calculator on me. So I had no way of solving this equation except by using Desmos to graph it. Now, the graph does help us, but we don't need to do it. We just need to find the 0. You always need to find the endpoints, and that's what we were talking about in this last problem, was the endpoints are what happens as the length approaches 0. Because it can't actually get to 0, but it can get as close as you want to 0. Or it can get as large as you want to, because the smaller h gets, the larger L will need to be to get to infinity. But in both of those cases, the surface area is going to go to infinity as well. And how do I know that? Well, that's a good question. How do I know that? I shall use Desmos again to convince myself of that, and you by extension. That is very hard to get a good window for. So this is the graph of the volume as a function of length. The reason I was struggling a bit was because the surface area equation, let's go back to it. Here's the surface area equation. And so what is happening as the volume stays constant well, as the volume stays constant, if L is going to 0, then H is shooting off to infinity. So that is going to make this guy shoot off towards infinity. Right, so as L goes to 0, this goes to infinity. Surface area. And then as L goes to infinity, this guy goes to infinity. So in both of these cases, as L goes to 0 and as L goes to infinity, the surface area also goes to infinity. So then our value that we found must be the minimum, because it's got to be smaller than infinity. And like I said, I struggled to find the minimum to put that in a window, but yeah. So this is the point that we're honing in on here. Alright, so I didn't mean to finish the optimization problem with such a stressful answer, but do you have anything else you want to talk about? Well, my partner just told me he's at Trader Joe's picking up eggnog yogurt, so unless you pose a question, I am going to sign off. Alright, thank you guys. I think it's only one of you now, but thank you both for being the only two to join me here. That was a lot of fun. We should do this again sometime. Now that you're always up for doing math, right? What else can you possibly do in this Christmas season? Have a good night.